Okay, well, we want to talk a little bit about laws of exponents. So, a squared cubed, now you immediately told me is a to the 2 times 3. And of course, most people know that 2 times 3 is 5. Is that right? No, it's 6, and that's how. I knew that. I wrote it down. I'm just pulling your chain a little bit because a lot of times people will add these. It's really easy to do if you're not careful. And if you don't know how to prove that this is right. Okay? Well, proof is easy. And, you know, we don't do a lot of proofs, formal proofs in pre-calculus. But you do need to know how to verify your rules and understand why they are. Okay, so the proof of this, and it's not a big formal proof, so that word shouldn't scare you. It is a pretty scary word. Proofs are tough. Well, that means a squared cubed means what? What's a squared mean? Means a times a, right?
Oh, yeah.
We have to accept that, right? Okay? That's a times a cubed. And what's that mean? Yeah, you know. Okay? Right? Well, now by your associative and commutative laws and all that stuff that we won't worry too much about right now, you know that you don't really need those parentheses if everything's a multiplication, right? You group these things in any way you want, and one way to group them is not to group them, which is formally not really valid, but everybody does it. Right? And what's that? It's a to the 6th, isn't it? Right? Alternative proof? We could have equally easily said that a squared cubed is a squared times a squared times a squared. Right? And of course that equals right? Which equals, I guess I'll write it out, but at this point you're kind of tempted to just put an ellipsis 3 dots down and say it equals ... equals a to the 6th, but we'll write it all out. And that equals a to the 6th, right? Well, that's really all you need to convince yourself of the laws of exponents that says a to the b to the c equals a to the bc, right? Now, if you want to prove this, well, you don't know what b and c are, right? And, you know, really, I should probably have used m and n because these proofs only apply if you have integer power. So, ouch, got to say a to the m to the n equals a to the mn. And really, at this point, we can only say that for counting numbers. because this proof works as long as you have counting numbers. Now, what are the counting numbers? Give me a number that you might use to count something. 2. Yeah. 2 hands, 2 eyes. Okay? 946. If you got 946 sheep in your herd, you just look at it and say, yep, that looks like 946. No, you can see 2. You can't see 946, but you can count them, right? Okay? Give me an example of a number that you wouldn't use to count things. -2, right? You don't count negative things. So counting them, you wouldn't use 0 to count things. You look out there and say, hey, there's 0 sheep in that herd. And somebody else says, what herd? You're crazy, and they kill you. Because they don't want crazy people in their group, right? People got killed over 0. I mean, yeah, it was a big deal. Why do you want to include that as a number? And then it wasn't long before somebody said, hey, we can do negative numbers too. I'm not sure anybody got killed over negative numbers. Once they got over 0, they said, okay, you know, you're crazy, but I see that there's a use for that. Or somebody else that I trust tells me there's a use for that. But what use is 0? Okay? It's more complex than that. I mean, you know, religion and stuff. Okay? As soon as mathematics gets mixed up with religion, you got a problem. Okay? Or politics. But anyhow, we got this, right? For counting numbers, that's numbers like 1, 2, 3, 4, 5. Because now we can say that, okay, whatever m is, a to the m Okay? Make sense? And how many of these do you have? There's no 3 in here.
Oh, I thought you meant like groups.
Yeah, there are n of them, right?
Yeah.
So you have n times. Right? And that has to equal then I mean, if you got m here, m here, m here, and you got n of them, then you got m times n. All right. So it could well be like on a test, I'd say, okay, prove this, just for 2 and 3. Okay? Then I say, hey, you want an extra point or 2? Prove this. Probably won't require you to be able to prove that, but it's pretty easy to write it down. Once you understand this, it's not hard to understand this, but it's a little more abstract. Okay? And if you can understand this, then you can verify at least whether the rule you're using makes sense. You multiply those exponents or you do add them. Okay? Okay, well, now this looks a whole lot like that. You got a 2 and a 3, right? But what are you going to do?
Add them.
You're going to add your exponents. Why? Well, you know that's going to be a to the 5th, but that equals a times a. multiplied by A times A times A, which is A to the fifth. Now it's clear why you add them. You got this many of them times this many of them. If you got 47 of these and 28 of these, you're going to have 47 plus 28, right? So A to the 2 squared times A cubed is A to the fifth, and now you know why. Okay? So your general rule is this. Linear laws of exponents. Okay? Now, another law that we looked at last time and you need in order to know why you're getting the results that you're getting when you make your tables of the basic functions is A to the negative 2 equals 1 over A squared. Now, why is that? This is a little harder to prove. Okay? In fact, in a sense, you can't really prove it, but I'm going to pretend you can. Okay? Why is it so, though? Why? Well, what's A to the negative 2 times A squared? A to the 0. It's not 0, it's A to the 0, but right. Okay? Okay? Right. Now I'm kind of waving my hands a little bit here, but A to the 0 is 1 because any number to the 0 is supposed to be 1, right? Okay? Well, we can divide both sides of the equation by A squared, right? And this is, of course, one of the rules for manipulating equations that I'm pretty sure you're good with. Right? And what's A squared over A squared is what? We divide a number by itself, what do you get? Yeah. How many A squareds are there in A squared? 1. Right? I'm sorry? A sample of what? Come in, help yourself. Sample of anything as long as nobody objects.
Anybody object?
Yeah, just go ahead.
Yeah. Go ahead, yes, we're going to stay right here.
Trying to see if there are any pathogens in here.
Yes, sir.
Thank you for letting us.
Yeah. Okay, so a to the negative 2 times 1 equals 1 over a squared. And what's a to the negative 2 times 1? Just a to the negative 2. Anything times 1 is that thing. So a to the negative 2 equals 1 over a squared. Okay? Make sense? So there's a reason for this. It's not just something that's handed down on a stone tablet. Okay? Okay. Now, other rules, and I'm not going to go through details on these, but I might well do it in class. So you're probably going to see it, but I don't want to be doing the same thing repeatedly. This video is going to be available to everybody. So if they want to see the details of this, they can. Okay? So I'm going to do a couple of others. What I'm going to do is a to the m over a to the n over a to the m equals, okay? And what's that equal to? Well, it turns out that's equal to a to the n minus m. Okay? And what's the square root of a times the square root of a? Think of a number. What's the square root of 25? Okay, so what's the square root of 25 times the square root of 25?
5 times 5.
Huh?
5 times 5. 5 times 5.
Yeah, which is?
10. I mean, no, not 10.
Yeah, you know what 5 times 5 is. It's 48.
No.
Okay? Equals 5 equals 25. Right? Okay, that's what a square root means. How did you know that the square root of 25 was 5? You knew that because you know 5 times 5 is 25, right? Square root of a number is a number you multiply by itself to get the number. So the square root of a times the square root of a has to equal what? So square root of 25 times square root of 25 equals 25. I bet you square root of 16 times square root of 16 equals 16.
That's equal to A.
And the square root of 4 times the square root of 4 equals 4. Right? The square root of 144 times the square root of 144 equals 144. There's a pattern. Okay? And the pattern is, if you multiply the square root of a number by the square root of that same number, you get that number. So square root of a times square root of a equals a. Okay? So since square root of a times square root of a equals a, square root of a must be a to the 1/2. Why? Now that the why comes from here. Why? Because what's a to the 1/2 times a to the 1/2? What do you do if you have a to the n times a to the m? You add the exponents, right? Now, we just proved that for whole numbers, okay? Or counting numbers, okay? We didn't really prove it for other kinds of numbers like fractions, okay? Or even irrational numbers. We're not going to get that technical. But the same rule applies here as applies to a squared times a cubed. You add the exponents. A to the 1/2 times a to the 1/2 is a to the 1, and that's a. Okay? Now, in general, a to the 1 over n is the nth root of a. Okay? Because the nth root, like the cube root of 8, is 2. Because 2 cubed is 8. Cube root of 27 is 3 because 3 cubed equals 27. And these rules aren't something that are disembodied from what you know about arithmetic. Now, you probably don't know what the cube root of 216 is, much less the cube root of 1728. Okay? Now, cube root of 728, everybody knows that's 12. Okay? But not something you really need to know, although that one is kind of useful. Okay? And 6 times 6 is 36. You multiply it by 6, you get 216. Yeah, you really probably ought to know cubes up to like cube of 8 or something, because it helps think about things. After that, cube root of 1,000, that's easy. It's 10. 10 times 10 times 10 is 1,000. Okay? And that's an easy example to remember, to relate to. 1,000 to the 1/3. It is also, this can be written as a cube root of 1,000. And it's 10 because 10 cubed is 1,000. Okay? And these are important rules that are a little harder to understand than a squared cubed equals a to the 6th, and a to the 2nd times a to the 3rd equals a to the 5th. The multiplying and adding of exponents, okay? This one's actually kind of easy to remember, whether you remember for sure why or not. Okay? Now, we could even say, well, no, I'm not saying too many steps. Okay, makes sense? Okay, so it's real easy to screw up laws of exponents. Okay? Now I want to get to the distributive law of multiplication over addition and common errors people make with that.